So, what I'd like to do next is to show the connection between the operators and the energy basis and what we can study in the position basis or the x basis. Um, so we're looking for this connection between the energy basis and the x basis. When we're working with the energy basis, we pretty much would just take a operator like A, and say we have the lowering operator acting on the ground state. We said it's just going to give us a 0. We can't get any lower in energy than the ground state. But now if we project the position basis onto the ground state, that's going to give us a wave function that will describe the ground state. So what we can do is we can write our lowering operator as alpha times the position operator plus I beta times the momentum operator, or if we put in what the terms are, m omega 2 h bar square root times position plus I divided by the square root of 2m omega h bar times the momentum operator. And now if we put in the values of those functions, or the shape of those functions in the position basis, then we have the square root of m omega over 2 h bar times just the position x plus I over 2m omega h bar square root minus I h bar derivative with respect to x. So then we can clean this up a little bit. Plus I times I is minus 1 times a minus gives you a plus. H bar divided by square root of h bar gives me h bar over 2m omega square root. Now times the position, the derivative with respect to position. Now let's go back to our variable y, which we said was m omega over h bar square root times x. So if we do that, then what we get is a, in terms of, instead of x, in terms of y. And so we would get y over the square root of 2, which looks a little bit cleaner, plus 1 over the square root of 2 d dy, which again is also much cleaner. So we've hidden all of those m omega h bar stuff into the y variable. Now similarly, we could get for the raising operator y over the square root of 2 minus 1 over the square root of 2 d dy. So, okay, so now we've written, in terms of the position basis, the raising and lowering operators. So, okay, what if we operate on them? So if we lower on the ground state, we said that was 0, and that's like saying y over the square root of 2 plus 1 over the square root of 2 d dy operating on the ground state is going to be equal to 0. And now if we were to take the product with the position, the position basis, then basically y with the ground state would give us the ground state wave function. So therefore, what we have is y over the square root of 2 plus 1 over the square root of 2 d dy times the wave function now, not in terms of x, but in terms of y. And that's equal to 0. And so we're left with, actually, well, we can factor out the 1 over the square root of 2. So now we've got a linear differential equation, instead not in first order, not a second order, which is the derivative of the ground state wave function with respect to y plus y times the wave function is now equal to 0. Okay, and this one we can solve without much trouble. Like so. If we integrate both sides, then we get the natural log of the ground state wave function, a constant of integration, which I'm going to call a sub 0, minus y squared over 2. And if I now make this into an exponential, then I get, I'm just going to call e to the a sub 0, e to the minus y squared over 2. This is, I can just call a constant again. So the wave function is a sub 0 e to the minus y squared over 2, which looks very familiar. This is what we had when we first started with the Schrodinger approach. And so we can get the normalization. So that's just psi star of the ground state times psi of the ground state integrated over y, which in this case is a0 squared e to the minus y squared dy, which is a Gaussian, which in this case would give us, if I look it up on my integral table, it would just give me okay, so you could work this out. Sorry, I'm not going to work it out. If I move now back to the x basis, what you get is a normalization constant, which is m omega over pi h bar square root. I'm sorry, to the fourth power, right here. Because this is basically a Gaussian integral, and the Gaussian integral will give you a square root of pi. Anyway, so but the point is, this is now my ground state wave function with respect to x is m omega over pi h bar to the 1/4 power e to the minus m omega x squared over 2 h bar. And remember that matches with what we had when we did it with the Schrodinger approach, because the Hermite polynomial for the n equals 0 was 1. So that disappears. If we want to get the wave function for the higher energy states, then we just need to use our raising operator. So we would have we would just apply the raising operator n number of times, square root, to the ground state. And if we now project it onto the position basis, we get the wave function. And so then the wave function is equal to 1 over the square root of n factorial times 1 over the square root of 2 times the, so if we find the wave function back again in the y coordinate, then what we would have is sorry, I get all my y's. So we would apply the raising operator, which we said was y minus d dy, and then we'd have to do that n number of times, and we would get the constant a, which was m omega over pi h bar to the 1/4 power e to the minus y squared over 2. So it's getting a little messy. Okay. But anyway, so the point is right now, what we have to do is to now basically take the derivative n number of times on e to the minus y squared over 2. And so then what you get is if I compare this, what you get is, let me rewrite it a little bit cleaner. So I said 1 over the square root of n factorial, 1 over, let's bring that other stuff out front, m omega over pi h bar, so the 1/4 power, 1 over the square root of 2, okay, so let's kind of pull some of this together. If it's the 1/4 power, then that's the square root of n factorial is just n factorial squared. So I have m omega over pi h bar n factorial squared. And then we have 1/4, 1 over the square root of 2, y minus d dy to the n power e to the minus 2. So now that normalization constant is starting to come together and match what we had when we did use the Schrodinger. So the Hermite polynomials have a recursion relation where the Hermite polynomial for the index n is e to the y squared over 2 d minus, not d, y minus the derivative of y to the n power e to the minus y squared over 2, which is what we got with the Schrodinger equation.